The speaker today is Professor Pham Tien-Son, and Professor Pham Tien-Son is from Vietnam, the University of Dalat. Recently, he received the 2020 Đạo Quang Bửu Prize for Ministry of Science and Technology, which is a national award for outstanding contributions in science and technology. So I would like to take this very rare opportunity to congratulate him again on this significant achievement. So please join me to welcome to his talk. So please, now this is all your space.
Okay. Thank you. Firstly, I would like to thank organizers for inviting me to give this talk. I don't know the screen is okay, or I can just last more if you. I don't know.
You can make it full screen. Okay, that's
this speaker. Okay. Today I would like to talk about openness, Hölder metric regularity, and Hölder continuity properties of semi-algebraic set value maps. This I work with Dr. Ja-hyun Lee from Pühn University, Korea. Okay, my talk. The contents of my talk is as follows. We have four parts. The first introduction, the second definitions, and results, main results in the third and the last one. Okay. In variational analysis, we know that three conditions, the following well known in variational analysis. The first, openness. The second, metric regularity. And the last one, Lipschitz Hölder continuity. Okay, we can see the books, the following books, and the references therein. You can check here. Okay, let's start with a long time ago, maybe 30 years ago. We have the following theorem by Pühn. So let F be a set value map, then three conditions, the following condition are equivalent. Okay, the first, F is open at a linear rate. Okay, and the second, F is metrically regular. And the last, the inverse map, a set value is pseudo-Lipschitz continuous, or sometimes we call F minus has the open property. Okay. So you can see if F is open at a linear rate, so we have here. Okay. The same time, Bockway and Zhang proved the following theorem. Let F be a set value map, then three conditions are equivalent. The first, F is open at an order rate for some P positive. F is metrically regular of order 1 over P, and the last one. Okay. I give some definition after. We know that it's easy to see that openness at a positive order rate always implies openness. Okay, but the converse is not true in general. For example, when we consider this function from R to this interval, so we can prove that F is strictly increasing. So F is open, but F is not open at a positive order rate. So open at a positive order rate is stronger is openness. Okay. On the other hand, in 1996, Snyder proved the following theorem. Suppose that F is a polyhedral set value map such that the rank of F is a convex set. Then the following are equivalent. The first F is open. That means F maps open sets into open sets, right? The second, the inverse F minus 1 is lower elliptic continuous. And the last one, the inverse map is elliptic continuous. So so this assumption polyhedral set value map is very important in this theorem. It's very important. Okay, but we can see that it's easy by definition. Polyhedral maps are semi-algebraic maps. So it is nature to study relations between the following notions for semi-algebraic maps. The first, openness. The second, Hölder metric regularity, and the last one. Okay. We have, so we would like to consider the following three conditions for semi-algebraic maps. Okay. Okay, so next I give some definition. Maybe is very well known in analysis. The first subset S in Rn is locally closed. If this bone closed bone intersect S is a closest in Rn for some epsilon positive. Okay. And let F be a set value map, then we can define the domain, the ranks, and the graph of F. And the same, we can define the inverse map of the map F, define it as follows. It's okay. Okay. So next, the map F is called lower semicontinuous if for any S is the domain of F and any Y belong to Fs, and for any sequence Sk tending to S, there is a sequence Yk, a subset of this tending to Y. So, and we said that F is open map from the domain of F into ranks of F if for every open set U in the domain of F, then the image is open in rank of F. Okay, so in the case if the domain and rank of F is open sets, so we said that F is open. Okay. The next is F is said to be Hölder metrically regular if for each point Y star belong to here, and for any compact set K, there is for some constant epsilon, C, and alpha satisfies this some inequality. Okay. Here this means the distance from S to this set. And when we fix Y equal to Y star, then we get Hölder metrically subregular. When you can see if we fix y star here. So we can see that the first condition stronger the second condition, right? By definition. Okay. The next, F is said to be pseudo-Hölder continuous if for each S star belong to the domain of F, and for any compact set K, this is constant C, epsilon, and alpha, such that the following satisfy. Okay. So in this condition, if we let S1 equal to S star here, then we can get the lower pseudo-Hölder continuous S1 equal to S star when we fix S1 here. So the first, this condition stronger the second condition, right? Okay, but the second does not imply the first condition, right? By definition. Okay, so the next, I give some definition of semi-algebraic sets and semi-algebraic maps. So a subset S of Rn is called semi-algebraic sets if it is a finite union of sets of the following sets. Here Fi and here Fi are polynomial. So this set, this finite union of this set. So this equation and inequalities, right? Yeah. A set value map F is said to be semi-algebraic if its graph is a semi-algebraic set. So it's easy to understand the definition. For example, the following, by definition, we can see that the following maps are semi-algebraic, piecewise linear, or piecewise quadratic maps. Of course, the polynomial or rational maps are semi-algebraic maps. So you can check. Okay. So next, let Fp a semi-algebraic map. Then we can prove that the inverse map F minus 1 is a semi-algebraic. And the following maps are semi-algebraic, this map and this map. Okay, we can, by definition and Tarski-Seidenberg theorem, we can prove. Yeah, but the proof is very easy, not so difficult. Okay, so okay, the first one I would like to present here. We call this the Laura-Swift inequality. This inequality very important, very important. So suppose that K is a compact set, compact and semi-algebraic set, and phi and phi and c semi-algebraic function, such that phi is continuous. Phi is continuous, and the second satisfy. The second maybe it's not familiar for you, but you can see that if C, sorry, okay, it's better. So this assumption, so, and we can see that if C is continuous, then this condition satisfied. Okay. Then two conditions satisfied. So we have the following: 0 of C, a subset of 0 of phi, if and only if the Lorenz-Smith inequality is satisfied. This just means this inequality is satisfied for any S belong to K, for some constant C, and for power alpha here. We can prove, see that if on the left hand side CS equal to 0, so phi is equal to 0. So if we have this inequality, then we have this relation. Conversely, maybe it's not true, but here we suppose that phi and C is a semi-algebraic function, okay? And K is a convex semi-algebraic set. So two conditions, this condition and this inequality are equivalent. This inequality very important in the following. Okay, so the first breakdowns. Let FP semi-algebraic set value map such that the graph of F is closed. Then F is a Hölder metrically subregular. Okay, so the this assumption very weak, almost without assumption. Okay, then the map F is Hölder metrically subregular. Okay, in order to prove this theorem, I use Lorenz-Smith inequality, and it's very easy. Okay, so I present the proof here. We fix Y star and a convex set K here, and we consider the following function, phi and C. Okay, then we prove that phi and C is by definition, we can check that this function is continuous, and maybe this function is not continuous, but satisfies the second condition in the Lorenz-Smith inequality, and it's easy to show that phi and C are semi-algebraic function. So by the Lorenz-Smith inequality, we can get you can see that F is Hölder metrically subregular. So the proof is very easy. Of course, I use here. Okay. The next, the second theorem. Let F be a semi-algebraic set value map such that the graph of F is closed. Okay, so we have the following equivalent. So F is an open map from the domain of F into branch of F, and branch of F is locally closed. So this condition is equivalent to the following. The first F is a Hölder metrically regular, and the inverse F minus 1 is pseudo-Hölder continuous, and the last one. Okay. The main point of the proof is to show the implication. The first imply true, the second true, the main point of the proof. In order to prove the first implies the second, I will use the Lorenz-Smith inequality again. Okay, and it's very easy. The proof, there are two steps here. The first, I prove that F is open if and only if if and only if the following function, this function is continuous. F is open, so we have this. F is open if and only if the following function is continuous, right? I would like to mention that this claim I don't need to assume that F here is semi-algebraic without this assumption. F is set value such that the graph of F is closed. Then we have this claim without semi-algebraicity. Okay, and the next I use the Lois-Smith inequality. We apply the Lois-Smith inequality to the following functions. The first, this function is continuous by here, and this function. Two functions, this phi and c, semi-algebraic function. It's not difficult to check and satisfy the Lois-Smith inequality. So from here, we can see that the map F is a Hölder metrically regular. So the proof is not so difficult. Okay. In the case single value, so we have the following. Let Fp continuous semi-algebraic map single value. Then we have the following equivalent. This corollary follow directly from the previous theorem. We call that F is continuous, so the graph of F is closed, and we can get this corollary. Okay, in the case single value. In particular, when m equal to 1, m equal to 1. If m is, so we have the following. Let Fp continuous function, not necessarily semi-algebraic. Okay, then the following are equivalent. The first F is open, and the second just mean F has there's no minimizer or maximizer. Okay, two conditions are equivalent. Okay, at this point, I would like to mention that in Pühn proof in this paper, this proposition under the assumption that F is a convex function. But here we don't need this assumption. And moreover, the proof is very easy. The proof is based on the following facts. The first, if S is a compact and connected set, in Rn, and because the F is continuous, so Fs is also compact and connected. Okay. The second fact, each compact and connected set in R is a closed and public interval. Then we can, using true facts, we can get this proposition. Okay. In the case, this okay. Sorry. This okay. The next, I would like to present to consider the semi-algebraic variational inequality. That means phi s belong to C, such that this inequality holds for on Y in C. Here F is, I suppose that F is a continuous semi-algebraic map. C is a closed and convex set, semi-algebraic set. And here P is a parameter vector. This well known in variational analysis, right? Okay. So let S, capital S, be the solution map corresponding to variational inequality Pi, and let capital F is normal Robinson map, normal map, defined by this. Here, PC is the Euclidean projection into the set C, okay, because C is convex, so convex and closed, so this function is well defined, okay. Then we have the following relationships, the first and the second. So this well known. Okay. In the following, for simplicity, we suppose that the domain and rank of F, the domain and rank of S, open sets for simplicity. So we have in 1996, Dontchev and Rockafellar group the following. Suppose that F is a fine map, This map, because F is a fine map, so F is a semi-algebraic map, and C is a convex polyhedral set, convex polyhedral set, so C is also a semi-algebraic set. Then we have the following equivalent, four condition equivalent. Okay, that is lower semicontinuous, that is pseudo-Lipschitz continuous, that is locally single value and Lipschitz continuous, and the so-called critical phase condition holds. Okay. The group recently Appl give a new proof of this theorem, a new proof of this. Okay, so here we can look this assumption. So I would like to change here. If F is a semi-algebraic map and C is a convex semi-algebraic set. So I would like to change this assumption. Okay. In their paper, Dontchev and Rockafellar asked whether the lower semicontinuity of the solution map as implies the local single valueness and Lipschitz continuous of S in 0K, okay, in 0K, in 0K JS. However, the following example gives a negative answer we have. Okay, so let Fp this function and C 2. Then the solution map as corresponding to variational inequality is given by this. Okay. So Okay, we can see that the map F is lower semi-continuous, but it is not locally single value and also not Lipschitz continuous around the origin in R2. Okay. Okay. You can look this function. If we identify the complex field with R2, so you can this function from, if you have the function from C to C, the complex field from Z to Z square. So this the first term is real of Z square, and the second, this means the image of the complex Z square. Okay, so we can prove that why F is lower semicontinuous. Here I prove that F the function F is open map from R2 to R2, and I use the next theorem. The next theorem implies S is lower semicontinuous in the neighborhood of 0. So this set there's 2 points, but when P equal to 0, so this only one point. But when P is non-zero, so this set is 2 points. Okay. And we have the first result in this section. The main theorem says that the following statements are equivalent. So the first the solution map is lower semicontinuous, and this condition equivalent to this and equivalent to here. So we have, and the first because the second and the third follow directly from the fourth. Okay, and this and this follow from this condition by previous theorem. So we have this condition is equivalent to the nine statements are equivalent. Okay. It's okay. This sorry, here I suppose that okay. I suppose that F is continuous semi-object map. C is closed convex semi-object set. Okay. In general case, here is the R5 case, but here is general case. In general case, we have moreover, you can see in this theorem, S is lower semicontinuous, so this corresponds it equivalent to pseudo-Lipschitz. Okay, here and here. Okay, this a 5 case, but in the 0 case, we need to change the Lipschitz by Hölder. Okay. in general case. Okay. By previous example, we see that the lower semicontinuous of solution map S capital S does not imply the local single valueless of S. Does not imply. However, we have if the solution map S is lower semicontinuous, then there exists integer n such that this we have this. This implies that the solution set is finite. That means this the solution the number of element of SP this set is finite, and moreover predict by the same constant. Okay, for NEP belong to Rn. So the lower semicontinuous does not imply the local single values of S. But we can see that this set is a finite set for NEP belong to Rn, and moreover we have the number of elements of SP less more than for the same less more than the same n. Okay, the same n. The proof here I don't want to present the proof here because the proof uses some tools from semi-algebraic geometry. Okay, if the function S is not semi-algebraic, then maybe it's not true. Okay. It's okay. Okay. The details of my talk can be found in the manuscript by Lee in here. Okay. Thank you very much for the kind attention. Thank you.
Okay,
Thank you
very
for the
much.
presentation.
Thank you.
So I suppose that everyone can unmute yourself to ask a question and for discussion.
Maybe not everyone simultaneously. Let me be the first one to try to ask a question. With the definitions used in this talk, openness, regularity, etc., the definitions are not quite standard. They are not completely local, not completely non-local. Why are you using this type of definitions? For instance, maybe these are okay, but when you define regularity or Hölder properties, okay, Hölder property.
Here?
Yes. Let me see. First, what's the role of alpha? In the definition, there exists alpha. Normally, when we are talking about Hölder properties, it is some kind of weakening the Lipschitz property, and we fix alpha. For instance, alpha less than 1. Here you are saying there exists an alpha, and in all the properties it goes this way. And another items which looks a little bit strange to me is this compact set K. What's the role of these two parameters, please? Alpha and K.
Yeah, thank you. The first, if alpha equal to 1, okay?
If it is fixed, my question is why you are defining these concepts, there exists an alpha.
Yes, alpha, because it consists Holder. In the case if alpha is 1, so this we delete a Holder here, right?
Yes. Let me be a little bit more specific with my question. You are then proving equivalence of certain concepts, regularity, openness, and the Hölder setting. And in both parts of this equivalence, you claim there exists an alpha. So in principle, alphas can be different. When you are in standard settings, Lipschitz setting or regularity setting, alpha equals 1. In all parts, it is the same. But in your case, they can be different, at least theoretically. Can they?
This is, if you put alpha equal to 1 here, so maybe the theorem is not in 0. Alpha depend on the function f. This exponent. Okay.
And also,
but then you claim equivalence, don't you?
Which result exactly are you talking about? Because I feel you're talking about some specific result, not just the definitions.
I think after this definition, you formulate a theorem claiming the equivalence of certain Hölder concepts. Can you please show this theorem?
Yeah. Here.
Okay. For instance, the equivalence of 2 and 3 both involve alpha, and theoretically they can have different values of alpha. Or
yes, maybe the second alpha in the second imply the same alpha here, imply here.
Okay. If this is the case, then this is a different statement. It's actually a stronger statement than the one formulated on this slide.
Yeah.
Okay. Thank you for the clarification. Yeah. And what's the role of K? Capital?
0K. Yeah. Remember that here I would like to consider global case, not local case.
Okay.
So I consider compact set K, and remember that here I define this belong to rank of F. Okay. So because I would like to consider the global case, not local. But how
my question is formal. Of course, there are classical definitions, also global ones, and they are not using anything like your K. So you need it for something, and this something is not present in classical equivalences.
Yeah. Here you can change for any incident when you fix S star. So for any S near S star, so you have local version. Okay.
Okay.
But in my talk, I consider global case, but the same situation.
But what if you drop this K? What is going to change?
What? Sorry?
If you drop, if K equals to the whole space, can it equal?
No.
Then no compactness.
No. It doesn't work. For example, when you look the rise with inequality, so
it comes from the Yelachevich inequality. Okay,
yeah.
I see.
If K is unbounded, so this inequality does not hold.
I see. Okay,
Moreover,
I think
in
I've
this
already taken a little too much time. Other people also want to ask questions. Thank you.
Thanks, Alex. So I saw Russell raise.
Okay.
Yeah. Hi, everybody.
Hey,
Thanks for the very nice talk.
congratulations for your talk. I'm just, I try to review the definition. This compact, capital K, it seems that the constant alpha, the Holder alpha, depends on K or not. In the same definition that you were discussing some minutes ago with Professor Kruger.
Sorry. This
In the definition of the property.
definition of
Yeah. Definition of Holder.
Holder.
Before. Before. Very.
Marco, closer to the microphone, please.
No, sorry.
We can't hear you well, Marco. Please speak into the microphone.
So I,
Yes.
Yeah.
The microphone is open. I don't know which is the quality of the sound. It's a little bit unstable. But my question is in the same direction that your question, Alex. No, constant alpha in the definition depends on the compact set K or not. I think according to the definition, it seems that the answer is yes.
Yes.
For each compact, there is a constant alpha depends on K.
Yes, of course, alpha depend on F, star, and K. Yeah. In zero, the exponent alpha depend on. Yeah.
Not because in the theorems in which alpha do not appear.
Yeah.
Okay. General with many statements are equivalent. I miss the presence of alpha of K, and so it's for me a little bit confusing. But okay, it's my problem. Don't worry. Another point, you said that the openness of one function f is equivalent to the property that f has no extremum points. You means global extremum points. Local, yes.
Yes, this open. Right. This theorem.
Not smaller.
the extreme.
I think it was for single valued mappings.
A single
Single
value
value.
map
Okay.
open.
Yeah.
About the extreme.
This
Scalar function.
What is one?
one function. Yeah.
This one. You say f little f is open if and only it has no extremum points. I suppose is my guess. You talk about global extremum points.
Yeah, globally. Yeah.
Or non-local. Okay.
This there's no f is open if and only if f there's no minimizer, local minimizer or maximizer. Local.
Even
And
local.
of course global. Local.
Thank you. Thank you very much. Thank you.
Russell?
Thank
Okay,
you.
hi. First of all, thanks for the talk. I was gonna make a short remark about your compact sets and the constants C and alpha, but Guyan already made the comment that those the constants in your Hölder regularity, those are going to depend on the compact set K that you have. So I don't know, maybe it would be better to call that boundedly metrically regular or something like on bounded sets, so that it's clear that those constants depend on the bounded sets that you're using in the definition. But that's just a small point. I wanted to ask, so you've got a result about equivalence of Hölder metric regularity and lower semicontinuity of the solution map, which I'm not sure, would Dontchev and Rockafellar have called that inner semi-continuity, because it's a set valued map. But my question was whether there's a characterization for when you just have metric subregularity. So what does that mean in terms of the lower or inner semi-continuity of either the solution mapping or the forward mapping?
Yeah.
Right. So you know, you've got metric regularity here. Is there a similar characterization for when you just have metric subregularity in terms of some sort of continuity property of the solution mapping?
Sorry.
So, right. So you've got equivalence of lower semi-continuity of the solution mapping, and Hölder metric regularity of the F mapping, for instance.
The proof is not difficult, but
right. My question is whether there's a similar notion of continuity of the solution mapping that either implies or is equivalent to Hölder Hölder metric subregularity of the F.
Subregular. In fact, you know that if F is a semi-algebraic value map with closed graph, then F is automatically Hölder metrically subregular without assumption, right?
Great.
Thầy câu hỏi là ông Russell ông hỏi là mình có kết quả tương tự cho metric subregularity hay không?
Mình hiểu, nhưng mà tự động nó subregular rồi, không cần phải giả thiết gì hết, không có cần tương đương. Em hiểu không?
Thầy nói đi thầy.
Here, if you put, for example, subregular here, okay, so automatically satisfy. Do you understand?
Yeah. Okay.
Yeah, I get that. I get that metric regularity is a much stronger property than subregularity.
Right.
My question is, when you weaken the regularity of F or the inverse solution mapping from metric regularity to metric subregularity, what is the corresponding continuity property that you get on the solution mapping? So, right. So start with the I don't know. Start with F being Hölder metrically subregular. What can you say about the continuity of the solution mapping? Yes.
No. Solutions. The solution map of always is Hölder metrically subregular. Okay. If the graph of a solution map is closed.
Mà chiều ngược lại sao thầy?
No. This condition S is lower semiconductors equivalent to this, but without this assumption, I don't need to suppose that S is lower semiconductors, but at always is Hölder metrically subregular.
So without the lower semicontinuity.
Yeah, without. Remember this theorem, okay? So if F is a semi-on-Z set value map, of course, solution map is always semi-on-Z map, okay? So this implies the solution map is Hölder metrically subregular without assumption.
Okay.
We change a capital F here by the solution. Yeah.
Isn't the question was about the condition on F when F is Hölder metrically subregular, and what can we say about the continuity property of the solution map with S and F different map?
Yeah, I kind of want to go back the other direction.
Please.
Yeah, I think the question of Russell was when F is Hölder metrically subregular, what can we say about S? So there are two different maps.
Okay, under this assumption, okay, if F is a semi-on-Z map and C is a semi-on-Z set, so this implies F is a semi-on-Z map. So the solution map here is Hölder metrically subregular. I need this assumption. Because under this assumption, so the solution map is always semi-on-Z map.
So
okay. I think Guayun had his hand raised at some stage.
Okay, thank you. I'm not sure you can hear me. First of all, thank you for the nice talk. Can I ask maybe just a simple question, continue on what Alex and Marco asked, is for the definition of the Hölder, I think it's metric regularity or metric subregularity, I couldn't remember, so let me see.
Hölder properties.
Yes, so as far as I understand, the exponent alpha will depend on the choice of the compact set capital K. But I want to know, is there any cases where you have a universal constant alpha that only depends on, say, the dimension of n, or maybe just the nature of your set value mapping capital F, not depends on the capital set K? Because, I mean, the reason I'm asking is that because, say, your capital F just defined as the lower level set of a polynomial, then the exponent would be just only depends on the degree and the dimension n, right? So I think if I'm right. So in that case, it will not depend on the compact set capital K.
Alpha, okay. You can look this inequality. So here, I'm not sure. I need to check my proof, but maybe alpha, because this maybe alpha here depend on K. Because alpha depend on phi and C, but maybe alpha depend on K. If K is like, I'm not sure. Maybe alpha. I need to check the proof, but I don't know. As the present, I don't know. But maybe I think that alpha depend on K. Also. Because you can see this inequality, this assumption.
So one last question, please. 1 minute left. Do we have another question?
no.
If no, then thanks to everybody for, and first of all, the speaker. Thank you for giving this nice talk, which you can see attracted big interest from the audience. Because of this complicated environment we are all in, we can finally do some mathematics and meet together at such online environment, which is not a bad thing. So anyway, thank you everybody. We've had a number of participants today. I'm not sure whether everybody is registered to get announcements about future meetings. Those who are not registered, please register at the website and you will get information about future meetings. Any more announcements? Hua? Back to you.
I think it's good for now. So thank you very much for joining. Yes, so you can find the link in the chat, the group chat.
The very last message from Vera contains a link. Please, those who are not registered, go there and register.
Yes. So the next speaker will be Michen Sarah, and after that will be Marco Lopez. So.
All today?
Pardon?
All today?
No. After 2 weeks.
Okay. We will have to wait a little bit.
Yeah, you have a little bit of break. So thank you very much for the speaker and everyone joining the seminar today.
And please volunteer to give talks at this seminar.
Yes.
Just email Hua or anybody, and we will arrange that. Okay?
Okay, thank you, everybody.
Thank you, everybody.
Goodbye.
Thank you. See you then.
See you. Bye-bye.